The other properties like kinetic stability of the complexes having T2G6 configuration octahedron complexes, particularly cobalt 3 plus complexes, rhodium 3 plus, and iridium 3 plus complexes could also be explained. And there are other thermodynamic parameters which could be explained, which we will discuss today. But before going to those parameters, the highlights of the crystal field theory, how it could explain various observed properties of the coordination compounds. Um, we Till now we understand that when the ligands in a particular symmetry, the number of ligands you know approach metal through in certain directions depending upon the coordination number and the symmetry of the complex to be formed. When they approach the metal ion, the metal starts sensing the approaching ligand field. The orbitals of the d orbitals of the metal are raised in energy. So when the ligands are far away from the metal, the metal does not sense the symmetry of the ligands. So all d orbitals are raised in energy in a uniform fashion. That is, the d orbitals remain degenerate uh, initially. When the ligands come more close to the metal, then metal senses that this ligand field is not symmetrical, is not symmetric, but it has certain asymmetry associated with it. The ligands are arranging, they are coming towards the metal in a particular directions, and there is an electric field gradient around the metal ion. And that is the time when the orbitals get splitted. Different orbitals, depending upon their orientations in the space, they feel different repulsions, and some of them feel more repulsion, they are raised in energy, and others who feel less repulsion are lowered in energy. So the berry center, the center of gravity, is that energy to which the d orbitals were initially raised. All of them were raised in energy initially, when the metal could not sense the symmetry of the ligands. So this process of splitting then uh, you know rearrange the d electrons in the d orbitals are rearranged into those subsets of the orbitals. And every electron which goes into the T2G orbital contributes to the stability of the complex by magnitude of minus zero point 0.4 delta 0 or 4 decals. And every electron that goes into the EG set destabilizes the complex by a magnitude of energy equal to plus zero point 0.6 delta 0 or 6 decals. So overall, the overall stability, crystal field stability, as the overall stability, given to the coordination complex by this rearrangement of the electrons in the separated orbitals, can be calculated by multiplying how many electrons are in the T2G set multiplied by this minus zero point 0.4 plus how many electrons are in the EG orbitals multiplied by plus zero point 0.6. So that gives the total energy, crystal field splitting energy or stabilization energy, what we call. And that's an important parameter, and that we are going to discuss today. So let's go to the presentation, make it more clear. Musarath, how many students have been admitted? अच्छा, तो स्क्रीन मेरा शेयर हो गया ना?
Yes, sir.
स्क्रीन शेयर हुआ है?
Yes, sir.
स्लाइड विजिबल है?
Yes, sir.
Yes, yes, sir.
Okay.
Yes, sir. Sir.
So here it is a crystal field stabilization energy. It is defined as the stability achieved by placing transition metal ion in a crystal field originated by the ligands arranged in a particular symmetry, and by virtue of this asymmetric ligand field, the d orbitals get splitted, and the d electrons are then rearranged in those splitted orbitals, and every electron which goes into the T2G orbital stabilizes the complex, and every electron which goes into the EG orbital destabilizes the complex. So overall stability is decided by how many electrons are in the T2G and how many electrons are in EG orbital. So it's a result of splitting of d orbitals in the ligand field. The electrons occupying lower set of the orbitals result in stabilization of the center metal ion of the coordination complex by an amount of energy called the crystal field stabilization energy. So crystal field stabilization in octahedron complexes when there are n x number of electrons in T2G and y number of electrons in EG orbitals, then the total energy of the electrons relative to the average energy of the electrons. What is the average energy? Average energy is the Barry center that initially all the six or five orbitals were raised to certain height. When the metal could not sense the symmetry, the asymmetry of the ligand field, so there was repulsion, but then all orbitals were raised in that. That's known as the Barry center, center of gravity or average energy, and is known as crystal field stabilization energy. This is minus 0.4 x times plus 0.6 y times delta 0. So this is the way how to calculate. This is the orbital energy, and here are three orbitals in the T2G, then two orbitals. This is 10 decays. This is every electron which goes here will be contributing plus destabilizing the complex by 6 decays or zero point 0.6 0.6 delta 0 or delta octahedron, or every electron which goes here will stabilize the situation. So this nothing new. So therefore, crystal field stabilization energy depends upon total number of electrons in d orbitals of the metal, that is x and y, total electrons, and not only total electrons, how many of them are in the T2G and how many of them are in the EG orbital. That information is also important. And what is the delta? These are numbers, x and y are numbers, but what is the value of the delta zero? Because this whole thing multiplied by delta zero. So ultimately, delta zero is important for crystal field uh, stabilization energy. Suppose you have two complexes, both contain same metal ion. So number of the electrons are same in both complexes. Say both of them are high spin complexes. So number of not only number of electrons are same, number of electrons in the T2G and number of electrons in the EG. They are also same because both complexes are high spin complexes. But one complex has moderate. This ligand field is moderate. It is slightly powerful than the other complex. So delta zero values will not be same, exactly same in the two cases. There will be some slight difference will be there between the ligand strength of the ligand field generated by two different ligands. So therefore, even if the metal is same, even if the complex form is both high spin or low spin, it is same. The number of total electrons is same. The number of electrons in the T2G as well as number of electrons in the EG is also same, but delta zero is slightly different. Even then, the crystal field stabilization will be different in the two complexes, right? So value of delta zero is important. Number is then distribution of electrons between T2G and EG, that already I said. So electronic configuration of the d orbit. Suppose you have one electron, crystal field stabilization energy is minus 0.4 into 10 into 1 delta 0, so it is minus 0.4 delta 0. You have 2 electrons, 2 in 4 into 8, you have 3 electrons, you have 1 minus 1.2 delta 0. These are the three situations where you don't have high spin and low spin possible. There is only one option, that electron has to go into the T2G orbital, because the electrons will be placed in these orbitals following the Ahuba principle, following the Pauli's principle, following the Hund's rule also, right? When you go to the D4, you have a situation now, you have two options. Either all four electrons have to be placed here, or all three electrons here, and fourth one will go to the EG. It depends upon strength of the electric field, ligand field generated by the ligands. If the ligand field is weak, then this thing will prevail. If the ligand field is strong, the splitting is huge, then this thing will prevail. So if this thing happens, then there will be 4 electrons in the T2G. So 4 into 4 is minus 1.6 plus pairing energy. Pairing energy is, if you place 2 electrons in the same orbital, they will feel repulsion between themselves, and therefore that will raise energy. Therefore, the pairing will happen at the cost of increasing the repulsion energy that is added. So overall stability is decreased by 1.6, and something will be subtracted, that is pairing energy. So pairing energy depends upon the nature of the metal ion, what sort of orbitals. As you go down the group from 3D to 4D to 5D, the size of the orbitals increase, and when the size of the orbital increase, the repulsion decreases. So pairing energy has lower value in the 4D as compared to 3D, and 5D has lesser value. So if the splitting is small, ligand field is weak, then of course it will go into this orbital. We will have T2G3 EG1. The crystal field stabilization energy will be minus 0.6 delta 0. So it depends upon, if you compare these two situations, which of the two will prevail. It depends upon the pairing energy. So, and it also depends upon the delta value. So delta value is dependent on the nature of the ligand. So pairing energy and delta value will decide which of the two things will happen, right? Let's go to the, so pairing energy for given element is fixed. So configuration, suppose you are dealing with a D4. D4 is manganese 3 plus, or for that matter chromium 2 plus, that is D4. So you have different complexes with different ligands. The metal is same, oxidation state is same. So ultimately, the pairing energy depends upon the nature of the metal ion and its oxidation state, etc. It is same chromium, but the delta value will change from complex to complex because it depends upon the nature of the ligand. So pairing energy for an element is fixed. So configuration adopted is actually determined by the value of the delta 0. For D4, T2G arises when delta is small, when the crystal field splitting is less, ligand field is weak, and this configuration arises when the ligand field is strong. Similarly, D5, D6, D7, we have high spin and low spin cases depending upon the value of delta 0. So if delta 0 is high, large, that means ligand field is strong, then low spin complexes will be formed. Pairing will be, the electrons will be paired in the T2G set, right? So this is the table showing for different configurations, different number of electrons. We have the configuration, say this is weak field situation and this is strong field situation. So D1, weak field and strong field are same because you don't have the choice. So one electron, it goes into T2G1, T2G, and minus 0.4 delta 0. So two electrons, same in the weak field as well as strong field. And three electrons, same, there is no difference. Similarly here also. The difference is high spin and low spin option arises in D4, D5, D6, and D7. So this is D4 high spin, ligand field is weak, so high spin complex is formed. There are 4 unpaired electrons, and 4, 3 is 12 minus 1.2 and one electron in the EG destabilizes by zero point 0.6. So minus 0.12 plus zero point 0.6 becomes minus zero point 0.6. So one electron in the EG orbital destabilizes the complex by a significant amount. The stability of the D3 is double than the stability of the D4. And when all electrons go into the T2G, the ligand field is strong. We have just two unpaired electrons, and the crystal field stabilization energy is minus 0.16 into plus P. Similarly, when you have D5, you have two possible configurations T2G3, EG2, and T2G5. In the case of D5, if it is high spin T2G3, the crystal field stabilization is zero because the stability achieved by three electrons in T2G is equally nullified by destabilization of the generated by two electrons in the EG. So there is no crystal field stabilization energy. Whereas if the complex is at the low spin, the ligand field is strong, all five orbitals are placed into T2G orbital, then it becomes 5 into minus 0.4. This is 2.0 and 2p means 2 times pairing energy because two electrons will be paired paired in the T2G orbit. Oh, नींद आती है यार क्लास पढ़ाते पढ़ाते भी then T2G6, T2G4 and EG2, 4 unpaired electrons. If it is high spin, the crystal field stabilization energy is, this is 4 into 4.4, it is minus 0.16, and 2 electrons in EG, that is 6 into 2, 1.2. So 1.6 minus 1.2, that becomes minus 1.4 plus pairing energy 1. And if all electrons are paired in the T2G6, there is no unpaired electron. It is diamagnetic situation, but crystal field stabilization energy is minus 0.24 plus 3p. Three electron pairs are there in the T2G set, so pairing energy 3 times. So similarly, D7, we have two situations, 3 unpaired electrons and 1 unpaired electron. The crystal field stabilization energy is minus 0.8 delta 0 plus 2p. Here it is minus 1.8 delta 0 plus 3p, right? If you want to find out what is the difference between the crystal field stabilization energy of a high spin and low spin complex of the same metal, let's say cobalt 3, cobalt 3 forming cobalt 2, D7, cobalt 2 forming high spin and low spin complex. What is the difference between the crystal field stabilization energy? So you take some difference of these two values. This is minus 1.8 and subtract zero point 0.8. So it is 1 delta 0 plus and 1 pairing energy. 3p minus 2p, 1p. So delta 0 plus p, that is the difference between the high spin and low spin. So it depends upon the value of the delta 0 and p. Delta 0 plus p. P is, having the destabilization impact, and delta 0 is having the stabilization impact. So it depends on the relative magnitude of the two. If the p is having larger value than the delta 0, then obviously high spin complex will prevail. If p is having smaller value than the delta 0, then the low spin complex will prevail. So D8, D9, and D10, these are the complexes which we don't have option. The number of electrons in the low spin is and high spin is weak field and strong field is same because configuration is same. So 210, it is also 210. So configuration T2G6 EG2 here, same here. T2G6 EG3 here, same here. So it is completely fit. So therefore the crystal field stabilization energy is same in all the weak field as well as strong field cases. So in the last situation, you have fire pairing energy, no crystal field stabilization energy. So this way, you can calculate the crystal field stabilization energy of any complex if you provided you know whether the ligand is a weak field or strong field ligand, and also you know the pairing energy. Now, pairing energy has two components. two terms. One is the Coulombic repulsion, that is, when you are placing two electrons with opposite spin in a small room in an orbital, they are bound to repel each other, and that is the destabilization process. So, right? And as I said earlier, as the size of the orbitals increase, as you go down the group, in any group, this pairing energy will decrease. This Coulombic repulsion will decrease. It will have a gradual decrease in any group. So that is true for the transition metal ions also, because the 4D, the orbital is bigger in size than 3D, and 5D is big, more, highest, larger, diffused than even the 4D. So as you go from 3D to 4D to 5D, there is gradual decrease in the Coulombic repulsion. So pairing energy should decrease as we go down from 3D to 4D in a particular group, right? The second component is exchange energy, right? What is exchange energy? When you have two electrons with parallel spin in any configuration, the electrons can exchange their positions because both are parallel, having parallel spin. So when you pair up the electrons in an orbital, that exchange is not now possible. So this is the exchange process stabilizes the situation. That's why Hund's rule says that the configurations with parallel spins are more stable than the configurations which are not parallel spin. That's why the nitrogen atom, in which the three electrons in the 3p orbital, there it is an exceptionally stable situation. So when you pair an electron into an orbital, you lose the exchange energy. There is loss of exchange energy, and that is directly proportional to the loss in the pairing energy, loss in the exchange energy, not pairing energy, loss in the exchange energy is directly proportional number of pairs with parallel spins. So if the number of pairs, electron pairs with parallel spin are more, there is more exchange energy. And if you decrease them by pairing, then obviously the exchange energy decreases. So largest loss in the exchange energy occurs in the case of T5 configuration, because this is the configuration in which each orbital has one electron and there are maximum unpaired electrons. So when you pair up the electrons in the D5 configuration, there is huge loss in exchange energy. So that's why manganese 2 plus, which is also in D5 situation, and iron 3 plus, which is also in D5, they prefer to have form in high spin. Given a choice, they will form high spin complexes because they have highest exchange energy, right? So these are the values for different ions. So T4 configuration, chromium 2 plus and manganese 3 plus. This is Coulombic, repulsion energy in kilojoules per mole. So this is 71 and 87. Look at the exchange energy; it's huge contribution as compared to the Coulombic repulsion. Coulombic repulsion is not as significant, does not have a significant contribution to the pairing energy. Total pairing energy is contributed generated by summing the two. So exchange energy makes the larger contribution to the pairing energy than the Coulombic repulsion. So the chromium 3 and manganese 3 have 244. Look at the D5. This has huge exchange energy. 5 electrons, unpaired electrons, 144, 194, and 237, right? And the corresponding values, Coulombic repulsion is comparatively less. Look at the D6. It has again, the values are not so high as compared to D5. And look at the D7. It has 87 and 100 and 123 and 150. So these are the values for Coulombic repulsion and exchange energy and the total, pairing energy. So these are different complexes. Then see chromium D4 pairing energies. This this was in the kilojoules per mole. The units here, it can be converted into centimeter inverse also. So this is wave number. So this is 18,800. The complex is this one. The ligand field is comparatively weak. It has 1300. The delta 0 has 13,900 value. Obviously, pairing energy is large than the delta 0, so high spin complex will be formed. Crystal field stabilization energy is minus 0.6 delta 0. Then go to the iron 3 plus. This is D5. See pairing energy, huge, 24,000, right? And water is a weak field again, 13,700. Again, high spin complex, no crystal field stabilization energy in the high spin state, delta Z. It is zero. Go to the D6, the crystal field pairing energy is somewhat less than the D5, and ligand field also somewhat less because it depends upon the nature of the metal ion. Here the metal is same, but then oxidation state is different. When you have iron 3 plus, delta becomes huge. Delta increases, and when you have iron 2 plus, it decreases down some. So in any case, the P is the dominant role, so high spin complex is formed in both cases. When you go to the hexa, cyano potassium ferrocyanide, it is again D6 iron in the plus 2 oxidation state, not in the plus 3. So now the delta is huge value because the ligand is now very strong, and pairing energy is almost same value because it depends upon the nature of the metal and the oxidation state, that is iron 2 plus. So because delta is now having large value, so it's now low spin complex form. Similarly, cobalt hexafluoride, the pairing energy is, in the case of cobalt, it's now cobalt 3 plus, pairing energy is somewhat higher and ligand field weak, so therefore high spin complex. Cobalt hexamine, pairing energy same, but then ligand becomes strong and therefore low spin complex. And cobalt hexaaqua, this is cobalt 2 plus D7, the pairing energy slightly higher and ligand field weak and high spin complex being formed. So now let's go to the uh, yes, this one, the applications of crystal field theory. So early success of crystal field theory was ability to explain magnetic and spectral properties of complex and basis for understanding and predicting a number of other structural thermodynamic properties that we are now going to discuss. One property was role of crystal field stabilization energy in the lattice energy. You can calculate and predict lattice energy by using a Born-Haber cycle, or the Born-Langes equation. If you have the values for the parameters, heat of formation, heat of some thermodynamic state functions, you can calculate the lattice energy, and then you can experimentally also determine the lattice energy, and you can calculate whether your theoretical value is matching with the experimental value. So prediction of the lattice energy is not highly accurate for transition metal compounds. The prediction is much better for sodium, potassium, calcium, manganese, and zinc than for chromium, iron 2 plus, cobalt, and nickel and copper. So these serious discrepancies are there. What we predict on the basis of the theoretical model that we have Born-Haber cycle, and what is the experimental observed value, there is huge difference between the two, what we calculate and what we observe. So this difference is attributed to the crystal field stabilization energy. Ions which have no discrepancy, there are some situations where the values that we calculate from the theoretical model are exactly the same that we determine experimentally. These are the metal ions: sodium plus, potassium, calcium plus, manganese 2 plus, and zinc 2 plus. And it was found later on that these are the metal ions which have zero crystal field stabilization energy. And when you have zero crystal field stabilization energy, the values that we calculate from the theoretical model are absolutely same that we obtained from the experiments. And for other metal ions where there is difference between the experimental values and the theoretical values, the difference when it was calculated, the difference was almost equal not always exactly, but very close to the crystal field stabilization energy. So ions which have no discrepancy are either having D0 configuration or D5 high spin state or D10, because it is in these three situations, D0, D10 and D5 high spin state, that you have zero crystal field stabilization energy, right? So let's energy, let us take the example of the let's energy of the halides of the calcium, of a series of the third period, which starts from the calcium and ends at the zinc. So which includes two elements from the S block and 10 elements from the D block, in which the metal occupies the octahedron voids. These are not the covalent compounds. These are ionic compounds, three-dimensional, 3D lattices formed by the halide ions, and then holes or voids are generated in that closed packed structure, and metals occupy the voids, octahedron voids. There are two kinds of voids or holes in the closed packed structure of the anion. One is the tetrahedron holes, and other is octahedron holes. These metal ions occupy the octahedron holes, and that means coordination number is 6. We expect gradual decrease in the ionic radius from calcium. When you go from left to right in a period in the periodic table, then we expect that the nuclear charge becomes progressively more powerful, and therefore it becomes, more, attracts the outer shell towards itself, and therefore the radius size of the atoms or ions decrease as you go from left to right in any period. This is general trend in the periodic table. So we expect calcium to be the largest atom and the zinc to be the smallest. And the because the size of the cation is an important parameter in the Born-Landis equation that's used for determining the Lattice energy. So because size decreases when you go from calcium to zinc, so correspondingly we will have gradual and smooth decrease in the Lattice energy when you go from calcium dihalide to the zinc halide, right? However, the smooth curve is not observed. We don't get a smooth curve. The calcium, manganese, and zinc, these three are almost on the straight line. Then others deviate from the straight line, and maximum deviation occurs at two places. That is vanadium 2 plus and nickel 2 plus. And halide is a weak field ligand. If we feel, if you talk in terms of the crystal field, which is an electrostatic model, we will say that the six halide ions are surrounding the metal when the metal occupies an octahedron hole, and we say that these six halide ions will generate an ligand field around the metal ion, and halide ions are weak field ligands, and therefore the vanadium 2 plus and nickel 2 plus, this is D3 and D8, has crystal field stabilization energy. Vanadium, for vanadium it is minus 1.2 delta 0, this is highest, and nickel also we have minus 0.12, which is highest. The other configurations have less, that is 0.6 and 0.8 delta 0, and D0, D5 and D10 have zero crystal field stabilization. So what sort of curve is obtained? This is the curve that we get. You will get this is for fluorides, right? So because the charge, size is small, the Let's energy increases, and then shows a huge hump here, and then goes down and then increases. So this is for vanadium, and then this is nickel. At two places we have maximum. But if you look at the calcium, manganese, and nickel, they are almost in one straight line, and they are smooth. So this deviation from the straight line occurs because of the crystal field stabilization energy. So more lattice energy. So there is some contribution from the lattice energy to the crystal to the lattice energy. For chlorides also same pattern is formed, observed. For bromide also same pattern is observed, and for iodide also there is a hump at the vanadium and there is another hump at the nickel. And because they are these two situations, the crystal field stabilization has highest value. right? So here is a situation where you can judge for yourself that crystal field stabilization energy makes a significant contribution to the LED's energy of the salts, right? The second thing is enthalpy of hydration of transition metal ions. When you dissolve a metal ion to the solution to water, it forms an aqua complex, and some energy is released. That energy is known as hydration energy. This hydration energy can also be, it can be called that it is the enthalpy of formation of this hexa-aqua complex. So the general reaction is expressed as you have the metal ion in the gaseous state, and then you add it to the water and you form an aqua complex. So delta H hydration, if you plot a graph between the hydration enthalpy and the atomic number of the 3D series, and you take the divalent metal ions, so you must again get a smooth line, but you don't get a straight line. If you subtract the crystal field stabilization energy from the observed values, you'll get a straight line. So what sort of graph is obtained? This is, yes, this is the delta H enthalpy change. Negative means more higher hydration energy. So this is calcium 2 plus having lower hydration energy. As we know that when you go from left to right, calcium 2 plus to the zinc plus, size goes on decreasing. When your size goes on decreasing, the hydration energy increases, and there should have been the smooth decrease like this, but it doesn't happen. There are two loops in the curve. One loop, it goes increasing, the hydrogen energy increases, and then comes to the down to the joins the smooth curve at manganese, and then again second loop increases, has a maximum, and then comes down. Manganese has a zero crystal field stabilization energy. Therefore, this manganese and zinc and the calcium, all three have zero crystal field stabilization energy. Therefore, they lie on one line. And, and this again, the maximum occurs at vanadium, which is T2G3, and at nickel, which has highest crystal field stabilization energy. So this thing again confirms that if you subtract the crystal field stabilization energy, all atoms will fall in one line. So crystal field stabilization energy makes a significant contribution to the hydration energy also. So two hump curve. Then if you record an ionic radii of the 3D metal ions, for both divalent and trivalent ions, there is steady decrease in the radii. For strong field case, until the T2G is reached, and for high spins at the when you have high spin complex, you have T2G3 half filled, and the next electron will go to the EG orbital. And if you have high spin situation, low spin situation, then all the electrons will go into the T2G until T2G6 is formed. So they will, any electron which goes into T2G will stabilize the situation and will decrease the size. And when you reach the T2G6 in the case of low spin complexes, next electron will go to EG1. And then because that EG orbital is directly confronting the d orbital, the ligands, the size will increase. The curves that will be obtained, this is the enthalpy curve. Yes, this is ionic radii. Look at this calcium. This should have been the normal curve. The ionic radii decrease because there is contribution from crystal field stabilization energy. Maximum decrease occurs in the case of vanadium, T3. This is high spin situation. And this is T2G3, EG0. The next chromium 2 plus is D4, T2G3, EG1. Therefore, size now increases. And then manganese, that size again increases because crystal field stabilization energy is zero. Then it starts again making contribution and it decreases. Nickel has highest crystal field stabilization energy, therefore size lowest, and then again increasing because crystal field stabilization energy decreases and becomes zero again at the zinc. This is for divalent Let's look at the trivalent. Yes, look at this. This is for the divalent current. This diagram is more clear. This is for this blank, hollow, is these circles are for high spin, and dark ones are for the low spin. So this is ionic radius going down, decreasing, and then increasing, right? Because uh, this is high spin situation. Electron, this is up to the T2G3. Now next electron goes to the EG. That increases the ionic radius. Then another one goes to another EG, because EG में दो orbitals हैं, तो एक और जाएगा. This is D5. This one. This is D4. This is D5 high spin state. So ionic radius. Then next one goes to the T2G. So size decreases. Next one again goes. This is T2G6, right? And this is T2G7, not T2G, this is D7, D6, this is D7, right? This again goes to the next one goes to the D8, this is D8. Next one goes again to the EG orbital, so size increases. Then again, this is zinc, the D10, again size. If you have low spin situation, then maximum occurs at the T2G orbit. This is for the divalent metal ions. And I have for trivalent also, same trend. These are 3 plus, same trend for the trivalent metal ions also, right? So yes. Now, stability of the oxidation states. कितना टाइम हो गया, मैं थक गया. 12:48. So एक इम्पोर्टेंट बात यह है कि कोबाल्ट, अगर आप साल्ट देखने जाओगे, कोबाल्ट का साल्ट ढूंढने जाओगे, तो सारे कोबाल्ट के साल्ट जो है, कोबाल्ट के दो ऑक्सीडेशन स्टेट्स प्रोमिनेंट हैं, कोबाल्ट 2 प्लस और कोबाल्ट 3 प्लस. जो साल्ट्स हैं, सभी का जो साल्ट आप स्टोर में ढूंढने जाएंगे, तो कोबाल्ट 2 प्लस का ही साल्ट मिलेगा. कोबाल्ट 3 प्लस का साल्ट आपको कभी नहीं मिलेगा. जैसे आप कोबाल्ट क्लोराइड ढूंढने जाएंगे, तो कोबाल्ट 2 क्लोराइड ही मिलेगा, कोबाल्ट 3 नहीं मिलेगा. उसकी वजह यह है कि कोबाल्ट की जो थर्ड आयनाइजेशन एनर्जी वो बहुत हाई है, right? If you want to remove first electron, it is lost easily. Second one is also lost. Third electron is not lost easily. It has very high value. Ionization energy is high. Therefore, most of the time, the cobalt 2 plus is very stable oxidation state, and you get salts in them. So much so that कि अगर आप कोबाल्ट 3 जबरदस्ती बनाओगे, तो उसको पानी में डालोगे. उल्टा है आयरन और कोबाल्ट के केस में. आयरन का अगर साल्ट आप बाहर रखोगे, अगर ढक्कन खोल के रखोगे फेरिक सल्फेट का, अगले दिन आप आओगे लैब में, वो फेरिक सल्फेट बन गया होता है. एयर ऑक्सीडाइजेस आयरन टू द आयरन 2 टू आयरन 3. वाटर ऑक्सीडाइजेस आयरन, पानी में आयरन पड़ा रहा तो फेरिक ऑक्साइड एकदम बन जाता है, रस्टिंग जिसको बोलते हैं. सो आयरन के केस में उल्टा है कि आयरन 2 प्लस इज वेरी अनस्टेबल एंड आयरन 3 इज मोर स्टेबल. कोबाल्ट के केस में उल्टा है. अगर आप कोबाल्ट 3 का कोई साल्ट बनाओगे जबरदस्ती और उसको पानी में डालोगे, तो एकदम कोबाल्ट 2 बन जाता है. Water is able to reduce cobalt 3 to cobalt 2. So cobalt 2 is unstable, stable, and cobalt 3 is unstable in water. So this is cobalt 2 plus, और इसको कोबाल्ट 3 बनने में नेगेटिव पोटेंशियल है. मतलब ये रिएक्शन बहुत नॉन स्पॉन्टेनियस है, ये कभी भी नहीं होगा, उल्टा बहुत जल्दी होगा. अगर आप कोबाल्ट 3, अगर इस रिएक्शन को मैं उल्टा लिखूं, कोबाल्ट 3 plus 1 electron giving cobalt 2 plus aqueous, this potential will be plus 1.3 volt, 1.383 volt. तो जितना पोटेंशियल प्लस में होगा उतना रिएक्शन स्पॉन्टेनियस होती है, और जितना नेगेटिव में होगा वो नॉन स्पॉन्टेनियस होता है. अभी इस रिएक्शन में नॉन स्पॉन्टेनियस है, क्योंकि पोटेंशियल जो है माइनस में है. So water reduces cobalt 3 to cobalt 2. So why is this happening? Because cobalt 3 का जो थर्ड आयोनाइजेशन एनर्जी है वो बहुत हाई है. लेकिन जो ही कोबाल्ट 2 को हम मैं साल्ट ले आता हूँ कोबाल्ट 2 का स्टोर से, पानी में डालता हूँ और कोई लिगेंड डालता हूँ, तो ये कोबाल्ट 2 खुद ही ऑक्सीडाइज होकर कोबाल्ट 3 बनाता है कॉम्प्लेक्स, ये लिगेंड की प्रेजेंस में। जब ये कॉम्प्लेक्स बनाता है तो कॉम्प्लेक्स स्टेट में एक्वा कॉम्प्लेक्स के अलावा जब लिगेंड थोड़ा स्ट्रांग हो, मॉडरेट भी हो, तो तब भी हमेशा कोबाल्ट 3 ही कॉम्प्लेक्स बनाता है। कोबाल्ट 2 का कॉम्प्लेक्स बनाना बहुत मुश्किल है, एयर इसको ऑक्सीडाइज करती है इस दौरान। तो अगर आपने ये बनाना हो जबरदस्ती कोबाल्ट 2 का कॉम्प्लेक्स, तो ये नाइट्रोजन का एटमॉस्फेयर देना पड़ता है, हवा को बिल्कुल एक्सक्लूड करना पड़ता है, वाटर को भी थोड़ा मतलब कम रखना पड़ता है। तो कॉम्प्लेक्स स्टेट में नटशेल में ये बात है कि कॉम्प्लेक्स स्टेट में कोबाल्ट 3 स्टेबल है और साल्ट में कोबाल्ट 2 प्लस स्टेबल है, या एक्वा कॉम्प्लेक्स में कोबाल्ट 2 स्टेबल है। जो ही लिगेंड की स्ट्रेंथ थोड़ी सी बढ़ा देते हैं हम, मॉडरेट से भी स्ट्रॉन्ग फ्री लिगेंड है तो तब तो हमेशा ही बनेगा कोबाल्ट 3 ही, लेकिन मॉडरेट लिगेंड भी हो तब भी कोबाल्ट 3 बन। ये देखिए एग्जांपल, कोबाल्ट 3 इज perfectly stable in presence of moderate to strong ligands. Difficult to prepare cobalt 3 आप बना ही नहीं सकते कॉम्प्लेक्स। ये देखिए ये कोबाल्ट 2 का कॉम्प्लेक्स है, यस, बिकॉज ऑक्सिलेट 2 नेगेटिव होता है, 3 ऑक्सिलेट हो गए 6 नेगेटिव, 2 प्लस, ये 2 प्लस है कोबाल्ट 2। इसको कितनी टेंडेंसी है कोबाल्ट 3 में जाने का, ये देखिए ये इज -0.57, मतलब पॉजिटिव तो नहीं है, लेकिन if you compare it with the aqua complex, इसको ये बहुत नॉन स्पॉन्टेनियस था, -1.83, ये भी नॉन स्पॉन्टेनियस ही है, लेकिन ई की वैल्यू बहुत हद तक पॉजिटिव की साइड खिसक गई है, राइट। इफ यू हैव phenanthroline which is an comparatively stronger field ligand, it becomes more towards spontaneous. If you have EDTA, और ज्यादा spontaneous. If you have ethylene diamine, और ज्यादा नजदीक spontaneous के, right? तो and if you have ammonia, और ज्यादा, और अगर आप cyanide हो तो this is plus now. हाँ, तो कोबाल्ट 2 अब ऑटोमेटिकली कन्वर्ट होगा कोबाल्ट 3 में। सो ये जो ये क्या नाम है, ईएमएफ था, इसको बोलते हैं ईएमएफ वोल्टेज, ये मैच कर रहा है इन लिगेंड्स की ऑर्डर में, स्ट्रेंथ में, कि जो लिगेंड जितना स्ट्रांग है उसका पोटेंशियल उतना पॉजिटिव साइड था। सो ऑक्सीडेशन ऑफ द कोबाल्ट 2 टू कोबाल्ट 3, it was later concluded that it occurs in 2 steps, कि जो अगर कोबाल्ट हाई स्पिन में होगा तो वो कोबाल्ट 2 में होगा, और लो स्पिन में जब जाएगा तो वो हमेशा कोबाल्ट 3 ही जाएगा। तो ऑक्सीडेशन takes place, this oxidation of cobalt 2 to cobalt 3 takes place in 2 steps. Number 1, the complex rearranges its electrons, it goes from high spin to the low spin situation, and then electron is lost. Rearrangement पहले हाई स्पिन स्टेट में होगा कोबाल्ट 2 तो T2G5 Eg2, ये लो स्पिन में जाएगा तो T2G6 Eg1, और फिर ये लूज करेगा एक इलेक्ट्रॉन और T2G6, ये कोबाल्ट 3 बना। दोबारा मैंने लिखा है कोबाल्ट 2 है तो T2G5 Eg2, फिर ये लो स्पिन में गया, T2G अभी भी कोबाल्ट 2 ही है, लेकिन इलेक्ट्रॉनिक अरेंजमेंट चेंज हो गया, और फिर ये ऑक्सीडाइज होगा, ये इलेक्ट्रॉन चला जाएगा, तो ये बन गया कोबाल्ट 3। यहाँ पे ये ऑक्सीडाइज होना क्यों आसान है, क्योंकि इसमें इस कोबाल्ट 2 लो स्पिन से लो स्पिन में बनाने के लिए ये इलेक्ट्रॉन जब लूज होता है तो सो दिस एक इलेक्ट्रॉन जब Eg से जाता है, देयर इज ह्यूज इंक्रीज इन द क्रिस्टल फील्ड स्टेबलाइजेशन एनर्जी, क्योंकि ये 0.6 डेल्टा जीरो का गेन हो जाता है जब ये इलेक्ट्रॉन को निकाल देता है यहाँ से, राइट। सो इसकी वो देखिए आप, क्रिस्टल फील्ड स्टेबलाइजेशन एनर्जी -0.8 डेल्टा जीरो प्लस 2p, इसकी है -0.18 डेल्टा जीरो प्लस 3p, और इसकी सीधा सबसे ज्यादा होगा -2.4, 64 is 24, 2.4 delta 0 plus 3p, right? There is huge increase, मैंने लिखा नहीं, यहाँ पे गलती हो गई, इसकी क्रिस्टल फील्ड स्टेबलाइजेशन बहुत ज्यादा है। ये एक इलेक्ट्रॉन निकाले 18 -1.8 से सीधा जाएगा 2.4 पे एक इलेक्ट्रॉन निकालने से। सो स्ट्रॉन्गर जितना डेल्टा जीरो होगा उतना ही लार्जर क्रिस्टल फील्ड स्टेबलाइजेशन एनर्जी होगी, और इसीलिए ये कोबाल्ट जो है +2 से ऑटोमेटिकली +3 में जाता है, राइट? सो सेकंड स्टेप इज एंडोथर्मिक, बिकॉज हाई आयनाइजेशन एनर्जी ऑफ द कोबाल्ट टू, लेकिन क्रिस्टल फील्ड स्टेबलाइजेशन एनर्जी बहुत ज्यादा होती है। देखिए ये 1.8 था, वो यहाँ लिखा है मैंने 2.4 + 3p, सो देयर इज ये gain in the crystal field stabilization energy favors ionization of the cobalt. Therefore, it becomes easy to form a cobalt 3 complex. So, इस सारी डिस्कशन का ये मतलब नहीं निकालना चाहिए कि क्रिस्टल फील्ड स्टेबलाइजेशन अकेला ठेकेदार है कोबाल्ट 2 को कोबाल्ट 3 में ले जाने के लिए. It is one of the factors, right, which is making a significant contribution here, but there may be other reasons also which may be influencing this ionization. So AMF इससे ये पता चला कि आप लिगेंड डिफरेंट यूज करके कोबाल्ट का 2+ से 3+ में लेने का जो जाने का टेंडेंसी है उसको ट्यून कर सकते हैं ये, और ये किससे ट्यून करेंगे आप? क्रिस्टल फील्ड स्टेबलाइजेशन एनर्जी को मॉड्यूलेट करके, और ये बहुत इंपॉर्टेंट हो जाता है जब आप ये, क्योंकि मेटल्स जो है ये रिडॉक्स, ये साइटोक्रोम्स, फेरिडॉक्सिन्स वगैरह, ये इलेक्ट्रॉन ट्रांसफर रिएजेंट्स भी है बॉडी में, बायोलॉजिकल सिस्टम्स में, तो वहां पे इलेक्ट्रॉन कैरी करना, एक मेटल का दूसरे मेटल को सिग्नल दे देना, उसका लिगेंड्स के साथ, डिफरेंट लिगेंड्स के साथ उनकी जो रिडॉक्स एबिलिटी है उसको आप मतलब ट्यून कर सकते हैं, कंट्रोल कर सकते हैं. दिस बिकम्स वेरी इंपॉर्टेंट फॉर बायोलॉजिकल एप्लीकेशंस. आज इतना ही, मैं थक गया, अब इसको कल कंप्लीट करेंगे. अब अपना अटेंडेंस बोल दीजिए.